Alright, well, welcome to Chapter 4. Today we're going to be doing two sections. The first section is very short, only a couple slides, and the second section takes up a good chunk of time. Alright, so the first section, we're talking about congruent figures, just congruent two-dimensional polygons, and we're going to be able to recognize congruent figures and their corresponding parts. That corresponding parts part is actually pretty important. So let's define congruent polygons first. Congruent polygons are polygons that have congruent corresponding parts. Now these two polygons right here are color-coded very nicely for us. So in order for this polygon and this polygon to be congruent, they have to have congruent parts. So all their angles need to be congruent and all their sides need to be congruent. So if this angle and this angle are congruent, and this angle and this angle are congruent, then these two sides must be congruent. All corresponding parts have to be congruent. So order matters. Even when we're naming, order matters, and we'll touch on that in a second. So as we go through it today, just think about what does it mean to be corresponding? Where are these two shapes related? So I want you to envision a triangle WYS and a triangle MKV. Maybe you'll want to draw those out, but the order does matter. So W and M are the same, Y and K are the same, and S and V are the same angle. Figure out what are the congruent corresponding parts, meaning which angles between the two triangles are congruent and which segments between the two triangles are congruent. See if you can pause it and try to think of a few. You should have 6 congruent corresponding parts by the end of it. Alright, either you have no idea what I'm talking about, or, which is okay, because we're just learning it, or you paused it and finished. So let's go over the corresponding parts. First of all, we have our congruent angles. Angle W and angle M need to be congruent. Angle Y and angle K, and angle S and angle V need to be congruent. So let's just see if I can create a couple triangles here to give you somewhat of a visual. So they do have to, well, those two, actually I'll erase that because that doesn't look good at all. They do have to look the same because they're congruent. Okay, good enough, just a little oversized. So we have W, Y, S. Now order matters, so I need to start in the same spot and go M, K, V. They have to be the exact same. So now we can see that angle W and angle M appear to be congruent. Angle Y and angle K appear to be congruent, and then S and V as well. So we have an angle, angle, angle similarity going on, which you'll learn later on in the probably chapter. Alright, now which segments are congruent? Hopefully you can see and notice. WY is congruent to MK. YS is congruent to KV, and finally SW is congruent to VM. So if all of that is true and they are in the correct order, then the two triangles are congruent. Let's get some more practice on that, including a new theorem. We have a third angles theorem. All this says, and we'll talk about why, it's a simple reason, but all this says is if we know 2 of the angles are congruent with each other, then we know that third angle between the two triangles also must be congruent. And the reason is because both triangles need to add up to 180 degrees, no matter how big the triangles are, so they purposely made those 2 different sizes. So let's say angle A and angle D were both, those look like they're about 50. So angle A and angle D were about 50. Let's say B was, that looks to be about 45. Okay, so angle B and angle E are 45. We have no flexibility for C and F because we know 180 minus 95 is 85. So angle C and angle F must be 85 degrees. So the third angle theorem says those third angles of the triangles are always congruent if their first two angles are congruent. Alright, Now let's prove that triangle AEB is congruent to triangle DCB. And yes, you will use the third angles theorem in this. So pause it and see what you can get. The key is to get all segments congruent and all corresponding angles congruent. So corresponding segments and corresponding angles congruent. Alright, assuming you've paused it and tried it, if you haven't, do it now. The first one is given. Angle A is congruent to angle D. So my strategy was, alright, none of the other givens include angles, so I'm just going to try to take care of all the angles right now. What can I do so I know that angle A and angle D are congruent? Well, I should also know that these two are congruent right here because of the vertical angles congruence theorem. Alright, well, if those two pairs of angles are congruent, then we just learned something about these two angles right here. Those have to be congruent because of the third angles congruence theorem. Notice my ordering. So this is going to be a big learning curve for us. My ordering was very important. Let's go to the vertical angles one. B was my vertex, so B was in the middle. That part's easy. But if I named this angle ABE, that means I started at A, I traveled across the three dashes, went to B, and then went back to E. So, what is the corresponding angle to angle A? Angle D. So I had to start the second one with angle D. Then going to the vertex through the three dashed lines, and then back to C. Notice how I even had to name it doing the same routes. That's very important. Let's look at the next one for the third angles theorem. I went from A to E to B. So A's corresponding angle is D, then down to C, then over to B. The order has to be the same. I could not, even though it's the same angle, I could not have named that BCD. Later on, that's really important. Here it's not so much. Maybe it's more semantics right now. But it gets you in the habit of always making it correct when we start talking about shapes, which we will later on in this section. Alright, next. We have all the angles taken care of, so let's move on to segments. Segment AE is congruent to DC, and segment EB is congruent to CB. That's given. Alright, and also, actually, I should have included the third given in there. That's my bad. Let's throw that in there right now. BA is congruent to BD. Okay, that's important because I need all three angles and all three segments to be congruent in order to say that the two triangles are congruent. So triangle AEB is congruent to DCB. Now let's look at the ordering of my last statement. Now this is where it gets important. A is first, so D is first. E is second, so C is second, and then B comes third. So I traveled across the one dash, so I'm going to travel across the one dash in my naming, A to E and D to C. Then I travel across the two dashes, so I got to travel across the two dashes and then back to the third. The naming of the two triangles follows their corresponding order. I hope that makes sense, but if it doesn't, make sure you write that down. Moving on to section 4.2. This time we're going to be able to prove two triangles are congruent by what we call the SSS and the SAS. There are about 5 different ways to do it, but we're just doing these two right now. SSS stands for side, side, side postulate. What we're going to do is show that if we can prove two triangles have all three congruent corresponding sides, then those two triangles are congruent themselves. We don't even need to know anything about the angles. If we just know that the three sides are congruent, then we know that the two triangles are congruent. In this, let's go here. So, what I did is I first created 3 random segments with given length. I can't mess with their length. This one is 3, the other one is 4, and the other one is 5. And then I made a random triangle. Now over here, I have the same 3 side lengths. According to that postulate, I should create the same exact looking triangle as this one over here. So let's try it out. Let's make it look a little bit different. Let's make sure our 3 is going downward. let's put our 5 on top here, and let's put I connected to H there. Okay, so I got to make a triangle now. So let's say, first of all, it looked like this. If I try to match 4 to it, I can't make a triangle there. Then this side length is no longer 5 and I don't have a triangle. So I got to swing it out a little bit. Okay, and I could go to the other extreme. Well, that's not a triangle either. So somewhere in the middle, I'm going to have a triangle. That is pretty close right there, and it looks like that's where it's going to settle. And if you look at it, both of these triangles are the exact same thing. H corresponds with angle, what does that look like? A C and a B. So we'll just call that B for now. But these two angles correspond. They are actually exactly 90 degrees. Because of the 3, 4, 5 relationship, which you'll learn later with the Pythagorean theorem, I know that these two angles right here are both 90 degrees. And then these two are something else. But because it's 3, 4, 5 and 3, 4, 5, so I have side, side, side congruency across these two triangles. I know that these two triangles, although just rotated, are the exact same thing. I cannot have a triangle with sides 3, 4, and 5 that look any different than these. It always has to end up that way. So that's just one example. So I didn't prove it because a proof takes every case into every scenario into consideration, but I showed it using that one case. And you'll be doing that a lot too. So if two triangles have the 3 congruent sides, and they correspond with their sides as they're named, then they're congruent. So let's look at the naming. A to B, D to E. That covers the red segment and starts at A, which is good because A is between the single dash and the 3 dashes, and D is between the single dash and 3 dashes. Then we go B to C and D to E. Then we cover the 2 dashes. Then obviously it would come back with the 3 dashes. So the naming was perfect on this example, which it should have been. It's the book. And it showed that order matters and it achieves the goal. So look at these two problems right here. Decide whether this congruent statement is true. Now this is really going to test your understanding of the importance of the order. So pause this video and check if LPS is congruent to triangle PLN and if triangle ACE is congruent to triangle BDF. Alright, assuming that you've paused it and given it a shot, let's see what we have. Let me go full screen here. Okay, so starting at L, first of all, let's just give it an initial test. What do we see? Well, I see 2 congruent pairs of sides. Well, I just learned side, side, side. Where am I going to find that third pair of sides? Time to dig into your memory bank a little bit. Look what I have here. Both of those triangles share that side. And what reason can I give that the side is congruent to itself? Because that's important. And that's the reflexive property. Hopefully you thought of that. So I actually have side, side, side congruence between those two triangles that share a side because of the reflexive property, making LP congruent to LP. So now we have to check order. So I have red, green, and blue. Let's travel across those. L goes to P. P goes to L. Okay, that traveled across the 3 dashes. That's good. And then, so L went to P, and then P went to S. So if P went to L, then L better be going to N, which is good because that means this first triangle went blue, red, and the second triangle went blue, red. So when it comes together, it's going to cross the green, and the order was good. So, yes. The answer is yes for that first one. Let's do the second one. So we have side, side, side congruency. Good. So now we just have to check the ordering. Is triangle ACE congruent to triangle BDF? Let's see. A to C, so crossing the 1 dash. B to D crossing the 2 dashes. I already know that they messed up their ordering. And then C to E went across 3 dashes, D to F went across 3 dashes. They got that second part right, but then when you come back on the 2, this one comes back on the 1. So the naming was wrong. So what I want you to try to do is to try to rename this so it was correct. ACE B F D would have been the way to do it. A is between 1 and 2, B is between 1 and 2. That's good. They had a good start. Now B going to D would be the same as A going to E. And then D to F, E to C. Oh wait, let me check that again. Let me go with the way they ordered it. So A going to C would be the same as B going to F. There we go. And then C going to E would be the same as F going to D. Alright, so order matters. The first one was yes, the second one was no because the order was off. Now pause it and try to determine, now it's going to take a little bit of work, whether triangle ABC is congruent to triangle DEF. And then I want you to explain using a 2-column proof. So have your statements on the left and your reasons on the right. Alright, so first reason, assuming you've paused it and tried it already, I just went with the given. AB is congruent to DE. That's nice. Well, how did I know that was given? Because they gave us those side lengths. What else is given? BC is congruent to EF. Alright, so I already have side. Now I need to figure out that third side. And that third side is pretty ugly because it doesn't share the whole thing. So we have to make sure the excess is the same. And how are we going to do that algebraically? Well, I need to include that 2 with the shared side and see what I can do. So AF, the measure, I don't have the segment sign above it. The measure of AF plus the measure of FC equals AC. So I want you to look at that and see that I just did segment addition. The measure of AF plus the measure of FC equals AC. What I am going to do, now what was my overall vision when doing that? I need to figure something out about that blue side right there, because that is the third side of one of those triangles. Next, I need to figure something out about this side that I know, because that's the third side of the other triangle, and in the end I need to make sure those are equal. So next step, just defining that green line, DF, DC plus FC equals DF. And I know this is a good idea because I have the same measure here and they share this side right there. So I know I'm on the right track. Alright, segment addition got me those 2 sides that I hope in the end are congruent. Now AF is 2 and DC is 2. I can say that was given because it's on the diagram. Next, let's plug into 4 AF and DC. So I just took out AF, put a 2 there, took out DC, put a 2 there. Now very conveniently, I have AC equaling 2 plus FC and DF equaling 2 plus FC. Then I already know they're equal to each other, making them congruent. So I can substitute AC in for 2 plus FC, because AC is 2 plus FC. So I can substitute their measures. Now if their measures are equal, then their size and shape are congruent to each other. So segment AC is congruent to segment DF. That was the third side I was trying to find. Now I have side as my reasoning right here. So side would be a reason. Triangle. Now let's name this thing. I'm going to start at A, and I'm actually going to call it ABC. You can name the first one however you want. The second one is where it gets tough. So angle A corresponds with angle D, and then angle B corresponds with angle E, and then angle F corresponds with angle C. So that is how you name triangles, and making sure their order is correct. Moving on here, we have a pretty simple including, if you called the givens two separate statements, this should only take you a total of 4 statements. If you call the givens one statement, it should take you a total of 3. So pause this and see if you can figure it out. Alright. So your first statement should obviously be, well, those two segments are congruent. And notice how they've been doing a very good job labeling, which is a good reminder for us to always label our diagrams as we move along and put them in our proof. So those two segments are congruent. Now I just need to find that third segment and make sure it's congruent to the other third segment. Conveniently for us, the third segment is itself because it's shared. So segment BD is congruent to segment BD. Reflexive property of congruence. It's congruent to itself. It's the easiest one in the book. But this is why that reflexive property is useful, because we still need to show that that segment is congruent to itself in order to have that side-side-side congruency be fulfilled. Now that we have side-side-side, and I should have actually probably, oh wait, we can use side-side-side now because we already learned it. So that reason wasn't good because I didn't have the angles written down. So you can only use the definition of congruent triangles when you have all the angles and all the sides congruent to each other. Now all we need is just 3 sides. We don't even need to know the angles, and our reason is side, side, side. So that was my mistake, but good thing I caught it. So triangle BCD and triangle BFD are congruent to each other. You must have an order that has B either first, middle, or last on both of them, and D either first, middle, or last on both of them. And then C and F need to be in the same spot also when you're naming. So there are different ways to name them, but you need to make sure that their order is corresponding. Alright, time to learn the last couple things here. Postulate 4.2. So we had side, side, side. Now let's learn side, angle, side, or as you will write, SAS. So, side, angle, side, and the way it's said is very important. We have a side, we have an angle, then we have a side. Down here, this is not side, angle, side, even though we have 2 sides and an angle, because this is side. The angle is not right here, so it's not side, angle. It is side, side, angle. Or angle, side, side. But if you think about it, you can realize why we don't do it that way. Alright, so that side, side angle will come up in a second, and I'll show you why that doesn't work, and we'll talk about it because it's also typed out, but I'd rather you see it. So, we have side, angle, side. If we have 2 sides being congruent to each other, and the angle between those 2 sides is congruent to the other angle in the other triangle, then we already know those 2 triangles are congruent to each other. So let's go here. Let's exclude that one on the right. So we have a side, an angle, and a side again. Side, angle, side. And we call this the included angle because it's between these 2. How many triangles could I make with this? Well, I can move this, but I can't mess with that size 10. I can move it quite a bit, actually. And I can move this, but notice when I move either of these 2, I'm messing with that angle. And remember, that angle is given to us. It's a certain size. So, let me create a triangle, and we'll talk about that. Actually, let's make it a segment. Alright, sorry about that. Here we go. Now we have that third triangle side length. And sure, let's have them show us its value. Alright, so his length is 7.95 right now. Let's say I wanted to create a different length right here. So I don't want it to be 7.95. If this congruency postulate is true, the 6, the 52.67, and the 10 will stay the same. As soon as I try to change his length on the right there, which it is changing, my angle measure changes with it. I cannot get back to, let's say we restart at 55 degrees or something. I cannot get back to 55 degrees unless I return back to that same side length, which was about 8. I can never get that back to 8 unless I'm at 55 degrees. They do work together, meaning if this is fixed, and this is fixed, this is also fixed because of that relationship created right here. And just imagine, let me hide this. If I have this sitting right here and a certain opening that stops up here, there's only one segment in the world that can finish this triangle because everything else is set in stone. Only this segment right here is going to finish that triangle. As soon as this moves, then I have abandoned what I said I was going to be true about it anyway. So that triangle is set in stone. The side angle side does hold true. Now, if you know the lengths of two sides, and I'm just reading this, if you know the lengths of two sides and the measure of an angle not included, remember this angle was included because it was between the two sides we're examining. This angle is not included. This one would have been included, but this angle is not included. You can create two different triangles, and they have it right there. Notice how AC grows a little bit, but AB and BC end up the same length. So I have two different triangles, and I'll show you how that works. Therefore, because we have two different options for the side-side angle, then there's not a special case for these triangles right here. There is a special case for right triangles. We'll talk about that. We'll call it the HL postulate. Okay, so let's go back to GeoGebra because I don't think that static proof is showing you anything. So let's get it dynamic here. Let's see. We have a side, and this 10 goes all the way from D to F. This G is just there for my convenience because I need to use that point to create a fixed angle. So I have a fixed angle 25 degrees right there. So according to that, I should, so side angle, and let's imagine there was only one segment that was going to satisfy this. So actually I need to make that a line. Bummer. This is where I want a line because I want it to go through point G primed. Alright, so I need to get this point down here to line up with point E. Where will that occur? Well, I can push it really far. Notice how my 6 hasn't changed, my 10 hasn't changed, and the 25 degrees hasn't changed. That's because I have side angle characteristics, and those three cannot change. I can push it really far, and right here, now I have a triangle. So, if I want to disprove this proof, or this postulate, then I need to find another way to make the 6, 10, and the 25 degrees hold true. Well, let me keep going. That's not going to work. Let me keep going back now. Now watch this. You should see that that line is converging onto point E again. And right there. So, I have side angle still, and this side right here is the one that changed. So, that's not true because I have two different scenarios where those characteristics could be true, and this is definitely not congruent to this. So, side angle does not hold true. And lastly, look at these 5 and you tell me if they are congruent. Now, they are not named, so do not worry about the order. Just say if those triangles are congruent, and that'll be the end of it. Alright, so hopefully you paused it and tried them on your own. Let me get full screen here. That looks good. Are these two triangles congruent? Well, I have side, angle, and then sharing a side right there. So yes, I have side, angle, side because of the reflexive property. How about this one? Alright, I have side, angle. So no, not necessarily congruent because you can't trust a picture. Because it's not side, angle, side, but it's side-side angle, then that's not true. This one is not congruent. Let's look at this one. We have side, angle, side. Side, angle, side. Yes. How about this one? Side, angle, side. Side, angle, skip that side. That's not going to look good. Side, side, angle. Well, we can't have side, side, angle. So no. And then finally, side, side, side. Side, side, side. Yes, that is congruent. So side, angle, side, and side, side, side are congruent. Side, side, angle are not necessarily congruent because there are two options for it. The best way to remember this, appropriate as it might not be, spell side, side, angle backwards, and you realized why we don't like to say that word in geometry. So I'll leave that with you. I'll see you in class. Hopefully these notes made sense, and we'll clarify anything that didn't. Answer the questions, and have a good rest of the night.